Welcome. So if you're in the right room, you should be here for Bayesian Statistics Made Simple. I'm Alan Downey. I teach at Olin College, which is in Needham, Massachusetts, just outside Boston. If you load up this web page, there are a few things there. One of them is the preparation for the workshop and getting some things installed. We'll get back to that in a minute. If you're currently working on getting things installed, you should stop, at least for a few minutes. If you're totally focused on installing software right now, you're going to miss the first half of the talk, and then you won't understand the second half. So don't do that. We'll get back to it in a minute. Don't worry, we'll be fine. The other thing you might want to do, if you load up this page, you'll see that my slides are there. If you go to the PyCon 2013, and at the bottom of that page, there should be a link to my slides. So if you want to follow along, the nice thing about having that up on your screen is that if I go too fast and I move on to a slide and you're not ready to move on yet, you'll have your own copy. So load that up. OK, here's the plan. So the first thing, I'm going to start out with Bayes' theorem and work our way toward Bayesian inference, which is the foundation of, whenever you hear about Bayesian statistics, Bayesian inference is the fundamental idea. The nice thing about this is that there's only one idea. If you get this, you understand the whole thing. Everything else is just applications of one idea. The particular thing I'm going to do is a computational framework for doing Bayesian inference. And this is different from the usual approach. If you sign up for Bayesian statistics at a university, they're going to start out with continuous mathematics. You do a lot of integrals. The math is not crazy hard, but it is hard enough that I think it's distracting. It's really hard to understand the Bayesian stuff while you're doing the math stuff. And my theory is that if you know Python well enough to write a few lines of code, you can focus all of your attention on the hard stuff without getting distracted by the easy stuff. That's the theory. In about 3 hours, you can tell me whether that theory is true. What we're going to do is a series of problems where I'm going to pose the problem, we'll discuss it a little bit, and then I'll have some exercises for you to work on, and we'll take breaks periodically. So here's the goal. In 3 hours from now at 4:20, you should be ready to take on a problem that's similar to the kinds of problems that we're working on now, and hopefully problems that are relevant to things that you're working on. You should be able to make progress on those problems after this workshop, and also have a set of tools that gets you ready to learn more on your own. And at the end, I'm going to give you some resources that you can go on and read more and learn more. So that's the goal, and again, in 3 hours, you can tell me whether we've got to that goal. Part of what I'm talking about today is based on material from ThinkStats. This is a book that I wrote and published about a year ago. It's available from O'Reilly. It's also available free under a Creative Commons license. So if you want to read ThinkStats, you can go to thinkstats.com. The whole thing is available in a couple of electronic formats. The other thing I'm talking about today is part of a work in process. And this is a book called Think Bayes that is at this point mostly done. And the draft is available from thinkbayes.com. So in fact, I would recommend after this workshop, your next stop should be to download the draft and read through that. Big chunk of what I'm going to be talking about today are examples from there. All right, here is all the prerequisite you need in order to understand everything that I'm going to do today. You have to understand conditional probability. So if we get through this slide, you'll be all set. So the first piece is just a bit of notation, which is I'm going to use P parenthesis A to mean the probability that A occurs for some kind of event A that either happens or it doesn't. So that's probability. And this is the notation I'm going to use for conditional probability. And that says the conditional probability of A given that B has occurred. So if I tell you that B is true, what's the probability that A is true? And then the last piece is conjoint probability, which is what's the chance that both A and B happen? And this says that, well, if I tell you that A happened, and you know the probability of B given A, then that's the probability of A and B. This is a variation of something that you might have seen. There's a simpler version of this that you see from time to time, which is that the probability of A and B is the probability of A times the probability of B. That's a simple version of this. That's based on the assumption that they're independent. If they're not independent, that's not true. This is the more general version. This is true all the time, even when A and B are dependent on each other. So that's it. That's the prerequisite. Now I'm going to do a little bit of manipulation here in order to derive Bayes' theorem. So the first step, I'm just going to write that definition that I gave you a second ago, but I'm going to write it in both directions, which is the chance of A and B should be the same as the chance of B and A. So I can write the two right-hand sides here, just two versions of the same thing. I'm not going to quite prove that those are equal, but I'm asserting that they're equal. And if you're willing to let me get away with that, then I'm going to write this equation, and I'm going to divide through by the probability of B. And having done that, I will have successfully derived Bayes' theorem. And this is it. This is the foundation of all Bayesian statistics. And what it gives you is the ability to go back and forth. If somebody asks you for the probability of A given B, you can figure it out by evaluating these three terms on the right-hand side. So in fact, you can think of Bayes' theorem in two ways. The simpler way is that it's an algorithm for going back and forth. If you want the probability of A given B, and for some reason it's easier to compute these other terms, then you can go back and forth. If you want the conditional probability in one direction, you can get it by going backwards. So okay, it's a useful tool. You can think of it as being a divide and conquer algorithm that says that if the thing on the left-hand side is too hard, you just evaluate the three things on the right-hand side and you're done. There's one other way to think about Bayes' theorem, and this really is the foundation of Bayesian inference, and that's the diachronic interpretation. Diachronic is Greek for through time. And what it means is that as you learn more data about the world, you update your beliefs about the world. So you can write, if you have a hypothesis, H, and you acquire some new data, what you'd like to be able to do is get from P of H, which is the probability of the hypothesis before you saw the data, to this conditional probability, P of H given D, and that's how strongly do you now believe in your hypothesis after you've seen the data. So it's before and after, that's why it's called diachronic. Let me give an example. If that's a little abstract, I think this example will probably make it clearer. And this is, if you've done a probability class, you've probably done lots of marbles in urns as a nice simple environment for talking about probability. I think it's much more interesting to talk about cookies in a bowl. It completely changes the complexion of the problem. So this is actually the Wikipedia page for Bayesian statistics started out with this example, and I borrowed it. So you've got two bowls of cookies. Both bowls have 40 cookies. In bowl number 1, 10 are chocolate, 30 are vanilla. Bowl number 2, it's 20 and 20. Your friend picks one of the bowls at random. Let's assume that that means 50-50, and chooses one of the cookies at random, meaning every cookie has the same probability of being chosen. And it turns out to be a vanilla cookie. What's the probability that you chose that cookie from bowl number 1? Okay, and this is standard. A lot of Bayesian problems have this general structure. So let's try to put this into the framework that I was just talking about. We have a hypothesis that the cookie came from bowl number 1. We have some data, which is that the cookie we chose is a vanilla cookie. And we would like to get, again, from this thing, which is called the prior probability, to this, which is called the posterior probability. So here are the pieces. We've got, how much did you believe this hypothesis before you saw the data? This term, this appears in Bayes' theorem up at the top, which is the probability of the data given the hypothesis. And that's called the conditional likelihood of the data. If this hypothesis were true, what would be the chance of seeing what we saw? That's what the likelihood is. If the hypothesis is true, what's the chance of seeing the data? And then the denominator of Bayes' theorem is what's the probability of the data under any circumstances at all? What would be the chance of seeing what I saw, regardless of whether my hypothesis is true or false? Now, in this example, we can plug in the numbers for all of these. So before you saw the data, there was a 50-50 shot that you had chosen either bowl, and so the prior belief that you chose bowl number 1 is a half, 50-50. The conditional likelihood of the data is relatively easy in this case because we were told that bowl number 1 contains 3/4 vanilla cookies. So if the hypothesis is true and we did draw from bowl number 1, then the probability of getting a vanilla cookie is 3/4. So that's the conditional likelihood of the data. And then the denominator is the total likelihood of the data. Now in this case, I particularly chose this example because the denominator is easy to figure out. In general, the denominator is kind of a pain, and we'll come back to it in a minute. But in this case, I have the same number of cookies in both bowls, and I chose one of the bowls randomly. So you can just think of it as being one big bowl. Every cookie had the same chance of being chosen. And if I add up all the cookies from both bowls, 5/8 of them are vanilla cookies. So the denominator in this case we can compute directly. Good so far? All right. Having done that, having figured out the 3 things on the right-hand side, you can turn off your brain. The good Reverend Thomas Bayes comes to your house and does the rest for you. In this case, just 1 multiplication and 1 division. And that works out to 3/5. So the numerator is the prior times the conditional likelihood of the data divided by the total likelihood of the data. And in this case, it works out to 3/5. Remember the 3/5 because we're going to come back in a minute. We're going to do the same thing computationally, and hopefully we'll get the same answer. So 3/5, remember that. All right, so that's our first example. Bayes' theorem using the diachronic interpretation. Here's the next stop. I want to start giving you this computational framework for working with Bayes' theorem. What I'm going to give you is an object defined in Python that's called a PMF. PMF stands for probability mass function. If you've taken a statistics class, you probably learned about PMFs. You can think of them as being a mathematical function, or if you're a Python programmer, I encourage you to just think of it as being a dictionary. A PMF is a dictionary that maps from all the possible values that might occur to the probability that each value does occur. So this is the first step of the framework. I'll give you a little outline of where we're headed from here. We're going to start with PMFs. A PMF, as I said, is basically a dictionary. It's just a wrapper around a dictionary. A little bit later on, we're going to define a suite, which is another object that represents a suite of hypotheses. We'll get to this a little bit later. And then we'll see a couple of examples where we inherit from suite in order to use this framework. So that's where we're headed. All right. So here's the point where we need to do a little bit of setup work. First thing I want to know is how many of you were able to get to the point where you can run install_test.py and it worked successfully? Okay, that's not bad at all. Here's what I'm going to suggest. First of all, don't try to fix it now. I really mean this. If you spend the rest of this workshop trying to get your installation working, you'll be very unhappy. The alternative, here's what I want you to do. Here's what I'm going to require you to do. Find a partner. Okay. And actually, let me ask you again. Raise your hand if you've got the environment working, and keep your hands up for a couple of minutes. Okay. If you were not able to get the environment working, check and see if you have a neighbor who did. If so, you've just made a new friend. If not, if you don't have either of your neighbors with a working environment, let's move until that's true. If any of you know Schelling's segregation model, this is exactly what we're going to do. If you have no neighbors with a working environment, you have to move. If you've never heard of this, you may now Google Schelling's segregation model. All right, so that's the deal. I'll turn around, I'll close my eyes for a minute. You all make sure you've got a neighbor. You can put your hand down, thank you. Make sure you've got a neighbor with a working environment. And take a minute to introduce yourself to your neighbor. Even if you do have a working environment, you're still going to introduce yourself to your neighbor. Because for all of the exercises that we do for the rest of class, you guys have to ask your neighbor. Anytime you have a question, you are required to ask your neighbor before you ask me. If you ask me, I'm going to ask, did you ask your neighbor? And if so, I'm happy to explain it to both of you, but I'm never going to explain anything to one of you. That's the deal. All right? So that's it. Now, I know that this is a really awkward thing because you all just walked into the room, you sat down, you expected to sit in a workshop and not have to be social. And I know how painful this is, so I thought we would just take a minute, turn to your neighbor, shake hands, introduce yourselves, and if you need a couple of icebreakers, here are a couple of things that you might talk about. what was your first computer? In my case, the first computer I worked on was a DEC System 20. I used to play Wumpus. What was your first programming language? My first programming language was BASIC on the Commodore 64. Actually, it's kind of like 6502 assembly code on the Commodore 64. And what's the longest time you've ever spent finding a bug that turned out to be a really stupid bug? And I'll let you guys can do your icebreakers in a minute. I'll just tell you my version really quickly. I was working at the San Diego Supercomputer Center. One of the programs I was running on the Cray. I managed to find a funny little bug in the Cray operating system that caused the entire system to crash every time I ran my program. And all the nice people who were trying to keep the lights on would have to come into the room and bring the whole machine up, and it took hours, and it was very, very bad. And so I told my boss, I'm positive that I fixed the problem. I'm positive that if you let me run my program again, it will not bring millions of dollars worth of equipment to a grinding halt and make the lights go out and flames come out of the back of the machine. So I ran my program again, and everything came crashing down, and flames came out of the back of the machine. And it turned out that I actually had fixed the bug. The program was now correctly working, but when I recompiled and relinked the code, the new executable did not successfully replace the old executable, and so I just ran the same stupid program again. So that was my embarrassing bug story. Take a couple minutes, talk to your neighbors, introduce yourselves, make sure you've got an environment and you're ready to do some pair programming, and we will resume in about 3 minutes. I know I've made a terrible mistake because now I've got you talking. I can't get you to stop talking, but all right, you have to stop talking? Okay, good, we're almost there. All right, so first thing I want you to do, now that you've got at least one working installation between the two of you, is to go into the directory where you unpacked the code that I gave you, and then let's just make sure that you can execute simple stuff using ThinkBayes. So thinkbayes.py is the module that has a lot of the code that I use in the book in it, and we're going to need that for the whole workshop. So you should be able to start a Python interpreter, and then import from ThinkBayes, you're going to import PMF, which is this class that I was just telling you about. So hopefully, again, that will work for at least half of you. Here's what that's going to look like, and as usual, if everything went well, then you should get no error messages. So if you print it, it should tell you that PMF is a class named PMF that's defined in the module named ThinkBayes. And if that's working, then let's do a simple example. We're going to make a PMF object that represents a six-sided die. So I said a minute ago that a PMF is a map from all the possible values that could happen to the probability that they will happen. So here's how this works. I'm going to create a PMF object named PMF. This is a slightly annoying notation, but the capital P means it's the name of the class. The lowercase p means that it's an instance of that class. And then I'm going to write a loop that goes for x in the values from 1 to 6. So those are all the possible outcomes of a six-sided die. And for each one, I'm going to set a value in the PMF where the value is x and the probability, at least for now, is 1. That's what that loop does. So I'll type that while you're typing it. Give me a good sense of how long this is going to take. Oops. Okay, so I instantiated a PMF object, and now for x in. So set is a PMF method that creates a new value in the PMF, and it gives it a certain probability. And if you now pmf.print, it will give you the list of all the values in the PMF and the probability associated with each one. Now, I said that it's a probability, but in fact, it's not really a probability yet, because in order to be a proper probability, they all have to add up to 1. And right now, they add up to 6, which doesn't really make any sense. But this is one of the easy ways to create a PMF, is you can start with almost any initial probabilities you want, and then normalize it. So if you use capital N normalize, PMF.normalize adds up all the probabilities and then divides through by the total, so that after you normalize the PMF, it will be a proper PMF where the probabilities add up to 1. So if you run print again, it should come back and tell you, OK, now the probability associated with each outcome is 1/6, or at least it's the floating point approximation of 1/6. So that's that. And that was actually the next slide. So we started out with an unnormalized PMF, normalized it, now it's all set. Now, I know what you're thinking as soon as you see all this code, which is, why am I writing code that is in violation of the most common Python style guide with all these capital letters for methods? And the reason is I developed a lot of this library while I was a visiting scientist at Google. And so I was working with the Google style guide rather than PEP 8. And now I'm stuck with it because it would be way too much trouble to change. And that means you're stuck with it. All right. So here's how we're going to use this thing. The general framework for doing these kinds of computational updates, we're going to start out with a PMF that is a map from each hypothesis to the prior probability of that hypothesis. And then we'll go through and for each hypothesis, we'll evaluate the conditional likelihood of the data and multiply the prior by the conditional likelihood. The result of that will be an unnormalized PMF, which we can then normalize, and the result will be the answers, which is what we want. You can think of that normalization in two ways. You can think of it as, well, my probabilities don't add up to 1, so I'm going to normalize and I will make them add up to 1. But what you're really doing there is dividing through by the total probability of the data, which is part of Bayes' theorem. So you can think of normalize as being dividing through by probability of data. OK, so try this out. Create a new PMF object. And we're going to create two possible values representing the two hypotheses. In this case, I'm going to use strings to represent the hypotheses. In general, you can use any kind of Python object as long as it's hashable. I need to be able to stuff these things into a dictionary, so it has to be a hashable type. But strings are. So I'm going to make a map from bool 1 to 50% and from bool 2 to 50%. PMF mult is a method that's going to look up this value and multiply the probability by this. Okay, so it's going to multiply the existing probability by a given multiplicative factor. So I'm going to take hypothesis 1, which is bool 1, and I'm going to multiply by the conditional probability of the data. The conditional probability of the data is this line here that says, what's the probability of a vanilla cookie from bowl 1? It's 3/4. The conditional probability of a vanilla cookie from bowl 2 is 1/2. So that's where 3/4 and 1/2 come from. That makes sense? If the concept of that makes sense, then what you've just done there is a Bayesian update. You've taken each of your hypotheses, you've multiplied by the conditional probability of the data, and if you now normalize that distribution, run pmf.normalize again, the result should give you the posterior probability for each hypothesis in the PMF. And if you print the posterior probability for bowl 1, ideally you should get the number that we memorized 10 minutes ago, which was 3/5. 3/5. So if you run this, ideally you will get 0.6. Yes, sir?
I'm still stuck on what normalized actually doing under the hood, but can you use your original example?
Mm-hmm. Repeat it so it's on the tape, which is, it's not clear what normalized does, because in the first example, when I normalized, all the values had the same probability. So it seemed like it just makes a uniform distribution. No. So what it actually does is just adds up all the probabilities and then divides through all of the probabilities by that total. So all of them get divided by the same amount, but if they didn't start out equal, they're not going to end up equal. The return value is what the total was. Was before I divided through. Okay, let me pause there for a minute. The summary of where we are so far, we've done Bayes' theorem, we've done the cookie problem, and we've introduced the PMF class. Let's take a breath for just a second. I'll pause for just 2 minutes, and I want to come around and see how things are going. And if you don't have a neighbor with a working environment, let's make sure that that's true. So we'll be back in 2 minutes. I think we're doing well. At least the groups who were willing to talk to me got to 0.6. A lot of people were just avoiding eye contact, and that's usually not a good sign, but we'll see how we do. All right, so let's do the second problem in this sequence. This is called the dice problem. So the theory here is that I have a box that contains a 4-sided die, 6-sided die, 8-sided die, 12-sided, and a 20-sided die. This is in fact true. I do have a box full of these dice. I used to play Dungeons & Dragons because I am that geeky. So yep, I have these dice, and suppose that I reach in and I grab one of these dice at random, and I roll it, and I don't tell you which die it was, but I tell you that I got a 6. And I ask, what's the probability that it was the 4-sided die that I rolled, or the 6, or the 10, or the 12, or the 20? So you'd like to, in general, be able to answer that question for any of the dice. So here's how we're going to do that. I'm going to introduce one more object called a suite, which is a version of a PMF. It inherits everything. So everything that a PMF can do, a suite can also do, but the suite is going to add some additional capabilities. I'll tell you about them in a minute. Here's how you should think of a suite. A suite represents a collection of hypotheses that are mutually exclusive and collectively exhaustive. Mutually exclusive means that if one of them is true, the others can't be true. And collectively exhaustive means that one of them has to be true. And if you take those two things together, what you conclude is that exactly one of them is true and all the others are false. The reason that that's a useful thing to assume is that their probabilities will add up to 1. And that's a useful property. Again, we're going to use a PMF, so you can think of this as being a map from each hypothesis to its probability. Here's what the suite object looks like. It's a class called suite. It inherits from PMF. It has an init method. When you initialize a suite, what you provide is a sequence of hypotheses. And again, you can use any Python object you want to represent the hypotheses. You just have to give me a sequence of them. What I'm going to do is I'm going to loop through all of the hypotheses that you give me, and I'm going to set the probability associated with them all to be equal, and then I'm going to normalize. So the default behavior of a suite is to assume that all of the hypotheses are equally likely, that the priors are all equal. If you don't want that default behavior, we can override it, but that's just the default. Quickest way to create a hypothesis is quickest way to create a suite is with uniform probabilities across the hypotheses. And in the case of the dice problem, that's exactly what we have. I said that I pulled the dice at random from the box. Let's assume that that means that they're equally likely. So I can create a suite that has this sequence of hypotheses. And in this case, I'm using integers to represent hypotheses. So the integer 4 means the hypothesis that it was a 4-sided die. And if you then print that suite, you'll see what we saw before. It should show you those 5 values, and each of them should have the same probability. So I'll do it while you're doing it. There's no such thing as a 10-sided die. Not in this problem, there isn't.
So then you're anti-D&D and all this stuff.
All right, so I created my suite. Again, I've got 4-sided, 6-sided, 8, 12, and 20. Each of them has equal probability, so it's 1/5. That's what I've got so far. All right, now I want to do a Bayesian update. In the cookie problem, we did the update ourselves. We went through each of the hypotheses, computed the conditional likelihood of the data, and used mult. What you find after you've done that a couple of times is that this structure happens over and over. Every Bayesian update looks like this. So here's a method called update. It's provided by Suite, and what it does is it takes some representation of the data, it loops through all the hypotheses. So for each hypothesis in self.values, the values are the hypotheses. I'm going to compute the likelihood, which is this likelihood function, and I'm going to pass the hypothesis and the data. This almost reads like the math notation, which is it's the likelihood of the hypothesis given the data. No, sorry, it's actually backwards, so it's confusing. It's the conditional likelihood of the data. So if I were thinking better, I would have done this the other way around. Anyway, likelihood of the data, given that the hypothesis is true, goes through and multiplies each hypothesis by its likelihood, and then renormalizes. So this structure is the same every time. The only thing that changes from one problem to the next is the likelihood function. So if you like, if you're into object-oriented programming, you can think of likelihood as being an abstract method. So the Suite class provides update, and what you're going to do is extend Suite. You're going to inherit update, and you're going to provide likelihood. That's how this is going to work. All right, so let's think about what that likelihood function should be. Well, let's see. We rolled the die, and we got a 6. So if it's a 6-sided die, what's the probability of getting a 6 altogether now? 1/6. Okay. What if it's a 10-sided die? What's the probability of getting a 6? 1/10. What if it's a 4-sided die? What's the probability of getting a 6? 0. Okay. So for all of those specific examples, it's pretty straightforward to compute the likelihood function. And now your job is to generalize this and say, for any m-sided die, what's the probability of getting any value n? And you're going to write a function to do it. So I've given you a framework in dice.py for filling this in. And I've put in everything except the likelihood function. So you're going to run the likelihood function. So let's come over here. So I'm going to get out of Python and ls. So one of the files that you got should be dice.py. And if you open up the editor of your choice, which is Emacs, you should find that there is a class named dice that inherits from Suite. And your job is to provide the likelihood function. As I said a minute ago, it takes a hypothesis and data. The hypothesis is an integer that represents the number of sides on the die. The data is an integer that represents the outcome of rolling the die. And what I've done here, I do this quite often in my likelihood functions. I often take hypo and data and unpack them into variables with better names so that I can remember what it is. So the number of sides comes from hypothesis. The outcome is the data. And your job is to write this method. What is the conditional probability of the data given the hypothesis? Kick it around, talk with your partner. I'll come around and answer questions if you need them. And then when you're ready to run it, if you run python dice.py, it should give you the posterior distribution. Now, currently it's not working because the likelihood function is wrong. So let me do the first half of this. If you're working productively and you don't want to listen to me, that's fine. If you're stuck, this might help get you unstuck. So the first piece, I figure, okay, if the outcome that I got is more than the number of sides on the die, well, the likelihood of that is 0. So that one's easy. The other case means, okay, I got something that's legal. Now the question is, if the number of sides is num sides, then what's the probability of getting whatever I got? 1 over num sides. And assuming that it's equally likely, right? And if you're using Python 2, which you should be for this, remember to throw in a floating point value whenever you do a division, because otherwise you get integer division, which in this case is not going to do what you want. So I think that'll work. Let me save that and run it. And let's take a look at this. So what gets printed here should be the posterior probabilities. So this is telling me after you've seen the data, this is the probability that it actually was a 4-sided, 6-sided, etc. What is the posterior probability that it's a 4-sided die? 0. And that makes sense because I have seen data that contradict this hypothesis. Therefore, it's impossible. Therefore, it has probability 0. This makes sense. The 6-sided die is looking quite likely. It has about a 40% chance. The 8-sided die is a little bit less likely. 12 is less likely, and 20 a little bit less likely than that. Certainly hasn't been ruled out. There's still a 10% chance, or 11, 12, that it's a 20-sided die. So it hasn't been ruled out, but this tells us now what we should believe about the dice having seen one roll and getting a 6. Any questions about that? Which part of it is counterintuitive? I understand.
But my gut says
Gotcha. I understand why it's counterintuitive. We're going to do a couple more things with this that might make it seem more believable as we go along, but I understand what you're saying, and I don't disagree. It's a little weird at first look. Okay, so you modified dice.py, and hopefully you got results that didn't look too different from mine. So here's what my solution looked like. And here's this is just the code that does the creating the suite and doing an update. The update, again, is the outcome of the die, and then printing the results. And these are the results that we just saw. Now, one nice thing about this framework is that as more data become available, you can just do multiple updates. So we don't have to write any more code. If I keep rolling the die, so let's say it's the same 6 that I rolled before, but now I roll it again, and I get a 4, and then an 8, 7, 7, and 2. I can do successive updates just like that. So you can do this actually while I'm talking. Go ahead and replace the line that used to say, update 6. In other words, just do one update with one roll. Replace that with this code to do 6 rolls. Now we can think a little bit more about the intuition. This might help a bit. If I've rolled the die 6 times, and I've never seen anything bigger than 8, I'm starting to think it's probably an 8-sided die. And if it were a 20-sided die, it would be mildly surprising to roll it 6 times without ever seeing anything bigger than an 8. So my expectation when I finish doing this update, certainly the 4-sided die has been eliminated. Now the 6-sided die has been eliminated because I've seen some 7s and 8s. I expect the posterior probability for 8 to be quite high and for 20 to be quite low. Yes, sir, in the back. Right. Okay, yeah, so depending on how you're doing this, if you're doing it from the command line, you might want to create the suite again. If you're running dice.py, then every time you run it, you'll get a nice fresh PMF. So either way, if you do the equivalent of these updates, worst case scenario, you'll double count the 6, and so your probabilities will be just a little different. So let me do that in order to give you a chance, and then we'll see the results. So here. Now, I'm going to cheat slightly here. I don't remember exactly what the roles were, but as long as I've got 6 of them and as long as the largest one is 8, it doesn't actually matter what the other ones are. And let me run it. So you should get something like this. Again, the 4-sided has been eliminated, 6 has been eliminated, 8 is now looking very likely, 12 is hanging in there. There's almost a 10% chance that it's the 12-sided die, but 20 is looking quite unlikely, less than a 1% chance that it's actually a 20-sided die. Again, I feel like that's stronger than I would have said.
Now I'm in the realm of the
Don't anymore. We've changed places. If you want the posteriors to be fairly certain, in other words, you know for sure what the truth is, yeah, you need more data. On the other hand, one nice thing about the Bayesian analysis is if you just have a small amount of data, then your posterior distribution will be wide in the sense that you don't know exactly what the result is, but it will contain the right information. And if you had to make bets based on the posterior distribution, they would generally be good bets. Okay, so that's the dice problem. Let's see if there was anything else we wanted to do with that. Nope, let's wrap up there. So just where we are so far, we got the suite class now. What the suite class provides is the update function. Almost all Bayesian updates have the exact same framework, so you don't have to change the update function. All you have to do is figure out the likelihood function, and again, the good Reverend Bayes comes to your house and does the rest of the work for you. All right, let's take a break for just a couple minutes. During the break, read about the German tank problem. Read about the German tank problem. You see that one of the things that the Allied intelligence officers were trying to do during World War II was figure out the capacity, the number of tanks the Germans had, and how fast they were making them. One of the ways they were able to estimate that was by looking at serial numbers from captured tanks. And if you're willing to make some assumptions about how the serial numbers are numbered, then you can make some inference. And that's exactly what we're going to do. We're going to do a slightly simplified version of it and a slightly more peaceful version of it, which is the train spotting problem. Train spotting is the hobby that some people have that doesn't really sound like much of a hobby, but it involves going to the rail yard and watching trains and writing down the numbers on the trains. I know, pretty exciting stuff. So let's say that you're a train spotter, and you have a prior belief about a certain freight carrier, like CSX. And you think that they operate somewhere between 100 and 1,000 locomotives. And maybe you have some background information that you know that the company is so big that that's how many locomotives you figure they probably have. So you go down to the rail yard, and you see one of their locomotives, and you see that it is locomotive number 321. The question is, what should you now believe, having seen that data? How many trains do you think they operate? Now, again, we're going to make some simplifying assumptions, and let's assume that they have some number n trains, and that the serial numbers on the trains are 1 through m. And that because of the way the trains move around, you are equally likely to observe any of their trains when you go down to the rail yard. So if you're willing to buy those assumptions, at least temporarily, then here's what we're going to do. We're going to figure out how many trains the company is operating based on the datum that we saw train number 321. So if you go to train.py and load that up, you'll see that, again, I've given you the outline of all of this. And once again, all you have to do is fill in the likelihood function. So I've got a class named train. Again, it inherits from suite. You have to fill in the likelihood function. And now here's the structure for doing the update. My range of hypotheses is from 100 to 1,000. I'm going to create a suite that contains those hypotheses. I'm going to update it with train number 321. And then I'm going to make a plot that shows what the posterior PMF looks like. So if I run it now, without doing the update, because right now my likelihood function returns 1 for everything. So my likelihood function right now is a no-op. It doesn't do anything. So if I run this code right now, I'm going to see the prior distribution, not the posterior. So let me run that. Prints the mean. This is a graph of the prior PMF. What it shows is across the bottom, those are all the possible values. This means I think they have 100 trains, 200, 300, up to 1,000. And this is the probability associated with each of those hypotheses. And initially, it's a uniform distribution. So all of my hypotheses are equally likely before I see the data. So now you're going to fill in the likelihood function and run this again. You'll see what the posterior looks like. Before you run it, I want you to think about what do you think it's going to look like? And if you want to, why don't you sketch it on a piece of paper, what you think the posterior will look like, then run the program and we'll find out. 321. You saw train number 321. So what's it going to look like for all the numbers from 320 down to 0? 0. You've eliminated all of those. So what's it going to look like for 321 on up? Think about it a little bit. Work on it. I saw some people sketching in the air. That's good. Excellent. Work on that. I'll come around. Oh, OK. At this point, there should be a certain amount of outrage as you realize that, in fact, the train problem is exactly the same as the dice problem. So let's see what that posterior looks like. So the people who were drawing swoopy curves in the back row were right. Good job, swoopy curve in the back row. OK, so we said before we looked at this, we've seen train number 321. And again, the assumption that we're making is that the company has trains that are numbered from 1 to n. So we've eliminated all the hypotheses from 320 on down. And that's why that looks the way it is. And now the most likely value, and this is, again, is going to be very unintuitive. The most likely value is 321. Because that's the value that maximizes the conditional likelihood of the data. If they had exactly 321 trains, that would give you the highest chance of seeing train number 321. If they have 1,000,000 trains, then the chance of seeing that particular train would be less likely. So this is counterintuitive and a little bit weird, but it is nevertheless true that if you had to guess how many trains they had, and you wanted to maximize your chance of getting it exactly right. So if you think of it like guessing how many jelly beans there are in the jar, then your best guess would be 321. But now think about it from the point of view of an intelligence officer. If you were asked how many tanks the Germans have or how many trains the Germans have, you would say, well, the most likely value is 321, but we should probably not plan on the assumption that that's true. What we would probably want to do, well, a couple things. You could think about, well, maybe the mean would be the right thing to look at. In that case, I could take all of these values and multiply them by their probabilities and add up that total, and that would give me the posterior mean of this distribution, which is exactly what you saw when you ran the program. The output there is the posterior mean. So that says, if I have to guess the average number of trains, then I would say they have about 600 trains. Now that sounds a little bit less crazy. If I saw a train 300, and I think they've got about 600, okay. Sounds like a kind of reasonable number. The other thing that you could do with this posterior distribution is think about, well, what would be the cost of guessing too low, and what would be the cost of guessing too high? And I could loop through the posterior distribution, figure out the cost of each guess, and minimize the total cost. And in fact, that's a common thing that you would do with, it would be a Bayesian decision analysis based on some kind of cost function. Okay, so that's the train problem. So we answered the second question, which is what the posterior distribution looks like. What if we spot some more trains? Why don't you try it out with some different data? Again, one of the nice things about this Bayesian analysis is that if you can figure out how to solve the problem with one data point, usually you can just loop in order to handle more data points. So let's throw that in. So down here, I need some people to generate some random numbers for me. So if they're definitely not running more than 1,000 trains. So you got to give me a number that's between 1 and 1,000. How many trains? What train did you see when you went down to the? And number 423. Okay. So let's do an update with those three numbers. So 3 of us went down to the rail yard. We all saw trains. We came back and we reported to each other. And now we can aggregate our data and come up with an estimate that takes advantage of all 3 observations. And notice the 2 things have happened here. One is that the distribution got pushed off to the right, because every time I see a new record high, the whole distribution gets pushed off to the right. The other is the distribution has become narrower, and that's partly because I'm starting to run up against my upper bound, but it's also because having seen 3 data points, I have more certainty, and therefore it's getting to be a little bit narrower. Yes, sir? That's a good question. One of the things that you can do when you start to see, oh, yes, might be wrong. And the answer is, yeah, I am starting to get a little nervous. And the reason is that the probability associated with the upper bound is pretty substantial. And that suggests that maybe there are other values out here on the right that I should have captured that I haven't. And the way that I might deal with that is by thinking about, well, where did that upper bound come from? And how confident am I? If I knew for sure that there's no way they operate more than 1,000 trains, then okay, I just have to live with this posterior and decide that it's right. But the alternative would be to go back and revisit it. Now, you're in a little bit of a danger zone when you start using the data to choose your prior, because now you're kind of using the data twice. You're using the data to choose the prior, and then you update your prior with the data. So we're into a little bit of a bogus zone, but just to see what it looks like. So here's the same distribution, but with a different prior. Or rather, same data, different prior. So that's what that comes out looking like. That's exactly right. Just to repeat that, it did not change the best guess, which is still whatever the highest number train was that you saw, right? But the tail now got stretched out farther. Yes, sir? Getting anything out of those lesser numbers? And the answer is no. Once you've seen train number 800 and whatever it was, you've eliminated all of those other contenders. And yep. I see what you're saying, and there is a certain logic to it. Now, changing the number of observations matters. So I'm not going to change the number of observations. Yeah, okay. But I am, right, I am going to change the lower bounds, which is, yeah.
That doesn't matter.
Yeah, so it turns out the only thing that matters is what was the highest number train that I saw and how many trains did I see. All the little numbered ones don't matter. And this maybe is a little bit counterintuitive as well. Even though I saw train number 1 twice, doesn't matter, it's not going to change the outcome. Memorize what this looks like. See, that looks the same. Now, I have to say, one of the other things that happens, all of these analyses are based on modeling assumptions, and this is something I'm going to talk about toward the end of the tutorial. If you actually saw train number 1 twice, what you might actually think is that one of your assumptions wasn't so great. We assumed that you were equally likely to see all trains. And these data would make you start to think that your model wasn't such a great idea. And so that's part of, you can think of the Bayesian update as being part of a small iteration. The small iteration is, see more data, update my belief. See more data, update my belief. The bigger iteration is, I chose a model that is the basis of all of my Bayesian updates. And as that model runs, I'm acquiring meta information about how this is going. And that might cause me to question my assumptions. So I've got this big modeling loop, which is, you know, those simplifications weren't so great after all. I'm going to start over with a different model. In fact, we're going to see an example of that later on. OK, now. So we answered the third question, what happens if we spot more trains? The last question, why we did this example, is I think this is a nice example of getting from nothing to answering a legitimate problem that mattered, at least during World War II, in about an hour and 20 minutes. And that's one of the nice things about this Bayesian analysis is you can do real work with remarkably simple tools on this stuff. Yes?
I mean, the example that we were
repeated is there are a lot of systems like load on a server where I see the high water mark at various points. And the question is, after I've seen 10 days and the high water mark is 70% of capacity, what's the chance that I'm going to go past 100% of capacity? You would want the model would be different, but the logic would be exactly the same. Very good. OK, done with the train problem. We're going to start in on the Euro problem. I stole this one from David Mackay. He wrote a great book called Information Theory, Inference, and Learning Algorithms. It's kind of a tough book because it is a David Mackay brain dump. It's a strange set of topics, but it's great stuff. His chapter 3 is about Bayesian statistics, and he poses this problem. This is an actual article that appeared in the newspaper, The Guardian, when the euro coins were first coming out. Someone noticed that the Belgian euro coin, for some reason, was a little bit more lopsided than most of the others. And so they decided to try it out and see what happens if you spin the coin on edge on a table and wait for it to fall over and count how many times it falls, heads or tails. And someone with too much time on his hands spun it 250 times, came up heads 140 times, tails 110. Took it to a statistician. The statistician computed what you might recognize as a p-value. The p-value is what would be the probability of seeing a result as extreme as that if the coin were in fact unbiased. And in this case, the p-value comes out to 7%. And so the conclusion of the statistician is, it looks very suspicious to me. And Mackay's take on this is, if we think of that data as being evidence that the coin is biased, how should we interpret that evidence? What he asks is, do these data give evidence that the coin is biased rather than fair? So that's the question we're going to take on. It's going to take us a little while to get there, but we will answer this question. I'm going to have to make some assumptions, as always. I talked about modeling a minute ago. We're going to do some modeling. So first of all, assume that the coin has some probability x of landing on heads. So if you spin it over and over and over, there is fundamentally some quantity that we're trying to estimate. And the object of the game is to figure out what x is. If you will bear with me, you should forget the fact that x is a probability. If you think of x as being a probability, your head is going to explode in about 15 minutes. Just think of x as being a physical characteristic of the coin. Any given coin has a weight, and it has a diameter, and it has a chemical composition, and it has some probability of landing on heads, which I'm going to denote x, and we're going to figure out what x is. We're going to do it in 2 steps. First is estimation. We're going to figure out for each possible value of x, what's the probability of that value of x, and then we'll come back to the question that Mackay posed, which is the probability that the coin is fair. For the estimation piece, we're going to use the sweet template again. And again, all we have to do is figure out the likelihood function, and then the good Reverend Thomas Bayes comes to your house and does the rest of the work for you. So here's your task one more time. If you go to euro.py, you'll see again that I've provided the structure for you, and you're going to fill in the likelihood function. The comments here explain the arguments that you're going to get. So you're going to get hypo. Hypo is going to be the hypothetical value of x, and this is on a scale from 1 to 100. So a little bit annoying, but there you are. And the data is going to be a string that's either H or T, capital H, capital T, for heads or tails, obviously. So you write the likelihood function, and then we'll get going again. Hypothesis, which is on a scale from 1 to 100, divided by 100. So now x is in the form of a probability. And now the question is, if I see heads, and the probability of heads is x, then what's the probability of the data? Don't be shy now. X. This is one of those questions where the answer turns out to be so simple that it's hard to believe it's that simple. But remember that while you're writing the likelihood function, you have the luxury of assuming that the hypothesis is true. You're computing the likelihood of the data given the hypothesis. So given that the probability of heads is x, what's the probability of heads? X. What's the probability of tails? 1 minus x. And that's it. That's the likelihood function for the euro problem. Yes, sir? So the question was, if it were a fair coin, it would be a 50-50 shot of heads or tails. So where is this hypothesis coming from? And I want to give 2 answers to that. And one of them is, again, while you're writing the likelihood function, you don't have to think about where the hypothesis came from. You can just take it for granted. In other words, someone tells you that this coin has a 60% chance of landing heads. And then they ask you, what's the chance of heads? It feels dumb, but you should just say 60%. But now, I think the reason you're feeling uncomfortable is that it's hard to imagine a coin that has a 60% chance of landing heads, or maybe that's contributing?
I'm not sure.
There's one part of this, and I think it maybe helps. The fact that it's spinning rather than being tossed in the air, at least it makes me feel better about the possibility that it's not 50-50. So if you spin a coin in the air, then it almost doesn't matter how the coin is shaped. It's pretty much going to be a 50-50 coin. But if you imagine something that's shaped like the lid of a can, or the lid of a bottle, jar is the word I'm looking for. Something that's a jar lid that's flat on one side and hollowed out. You imagine that's going to land flat side down some great majority of the time. And so you can imagine that there certainly could be coins out there where X is significantly different from 50%. Right, and we're going to get to, in a minute, we're going to define the prior belief about this. In fact, we're going to do two different priors for this, based on different background information about what coins are like, and I think that'll help. Okay, good. All right, so there's the likelihood function. That means we should be able to run this thing now. And let me just remember what the data is. Oh, sorry, I haven't got the update yet. We need to do one more thing. So here is my prior belief. And now before I call it, let's do suite.update. And let's give it 1 heads. And I forget, have we looked at the prior? We didn't look at the prior. Let's do that. Okay, so there's the likelihood function. We're going to start out with a uniform prior. And this is going to be kind of silly. So we're going to start silly, and we'll come back and be more realistic. I'm going to assume initially that I have no idea what X is. It could be anything from 0 to 100. So this coin might have 0% chance of landing heads. It might have a 10% chance of landing heads. It might have a 50% chance of landing heads. I'm going to claim that those are all equally likely. And here's the code that creates that prior distribution. And here's what that prior distribution looks like. All right, now we're ready to do the update. So let's say I flip the coin once or spin the coin once, I get heads. So we're going to add that to the code and then see what the posterior looks like. Again, you might want to think about what the posterior looks like. And one way to get started on it is to think, well, if I've seen heads, then what's the chance that X is 0%? Yeah, if the probability of heads is 0, and I just saw heads, then I've seen something impossible, and therefore that hypothesis can't be right. And now think a little bit about what the rest of that distribution looks like. Let's run the code and find out.
Next question.
Sure. Let me run this again. This is still the prior. I haven't done the update yet. So these are the values of X from 0 to 100. So 0 means no chance of being heads. 50 means fair coin. 100 means always heads. And initially, they're all equally likely. Now I'm going to do the update. And one of the things we know about the update is that since I've seen heads, 0 is now impossible. So this line will definitely go through that point. Let's think about what the rest of that curve looks like. Yeah, let's look at it. So I'm going to uncomment this line. And let's see the posterior. Oops. Something went wrong. That's the nice thing about having 50 people watch you program. All bugs are shallow. All right, there's the posterior after having seen 1 heads. As we expected, 0 has been ruled out. The low likelihood range has a low posterior probability, and if you went into this experiment thinking that this was a double-headed coin, then you would come out of it thinking, yeah, that hypothesis is holding up pretty well. Okay?
Agreed. Like if
and see what the posterior looks like. And tell you what, I'm gonna run through this in my slides. You all can do it live. So this is what it looks like after 1 heads. If you do another update, meaning 2 heads, should come out looking like that. 0 is still 0. 1 is still the most likely value, but it's becoming more and more biased toward high values of x. And in fact, the previous curve was a line. I multiplied it by x. It's now a parabola. So if we were doing this with the continuous mathematics, it's actually not that hard. These are just polynomials. All right, let's do one more. So I flip it a 3rd time, and now, oops, tails. You think about what that's going to look like. If you want to think about it mathematically, it's now a cubic function. If you want to think about the endpoints, so now that I've seen tails, x equals 100 has been ruled out. So the curve had better come back down to 0. And in fact, that's what it looks like. Now this is starting to look like a posterior distribution in the sense that I've got a sort of non-trivial maximum value. Where do you think that maximum likelihood estimation is right now? 2/3. And in fact, we've seen 2 heads out of 3. So the maximum likelihood estimate is in fact the exact proportion that we observed. But the nice thing is that the width of this distribution now gives me a way to think about how uncertain am I about that. And you can see, actually 20 has not really been eliminated here. 40 is a pretty good candidate. 40 is almost as good as 60. And I haven't really ruled out 80 or 90 either. So again, I haven't seen a huge amount of data, and this distribution reflects the fact that I'm still not very sure about x. Let's get some more data. So here's a simpler way to write that loop if you want to. If you give it a string of values, you can give it 7 heads and 3 tails, or do whatever combination you want. And then do the updates. If I see 7 heads out of 10, I expect the central tendency of this distribution to be about 70%. And I expect it to be a little bit narrower than the one I just saw, because I've seen more data. And in fact, that's what I get. Still pretty wide, but at least it's narrower than it was. But now we're ready to do the full-fledged version with all the data. And here's a shorthand little Pythonic way of constructing a string that has 140 heads and 110 tails. And if you run that code, that will give us our posterior belief about x after having seen all the data. And again, the central tendency will be the observed proportion. 140 out of 250 is about 56%. So that's where I expect the center to be. And I expect it to be a little narrower than the previous one, which it is. It's a little pointy at the top. It looks like the Washington Monument. That's just because I broke up this range of values into just 100 values. I could have done 50 values. I could have done 1,000. So that was an arbitrary choice. If I want to make this curve nice and smooth, I can just start out with fractional values of x. But that's what my posterior looks like. So at this point, I think that x is about 56%, but the range is still maybe from 45 up to about 65. Okay? So now what? We're in a little bit stuck here, which is if somebody asks me, what should I believe about x? I can answer that question. I would just show them the posterior distribution. But if I had to summarize it, it's not clear exactly how I should do that. One thought would be, well, the original question was, is this a fair coin? So I could just look in this PMF and say, well, what's the probability that x is 50%? It's tempting to ask this question, but it's not the right answer. You can do it. So PMF has a prob function, or method. You can give it 50, and what you find out is that, okay, there's about a 2% chance that this coin has exactly x equal to 50%. But I mentioned a minute ago, I could have divided this range up arbitrarily. If I had given it more values, that would be a lower number. If I had given it fewer values, it would be a higher number. This is not a meaningful number. So one alternative, I've been talking about the maximum likelihood estimate, the MLE. That just means I'm going to go through the posterior distribution and find the value that has the highest probability. And again, if the game is to guess what x is and maximize your chance of being exactly right, then okay, you would say 56%. And that might not be a terrible way to summarize this distribution. An alternative would be to use the mean. In this case, because it's kind of a narrow distribution and it's a nice symmetric distribution, the maximum likelihood estimate and the median and the mean are all about 56. So again, might not be a terrible answer. Probably a better answer would be to give a range of values. So one possibility is to compute the 5th percentile and the 95th percentile. The 5th percentile says that I think there's only a 5% chance that it's less than this. The 95th percentile says I think there's only a 5% chance that it's greater than this. So everything in the middle must be 90% of the posterior probability. So if I compute the 5th percentile, that's 51. The 95th percentile is 61. And together, those things constitute a 90% credible interval. Credible interval is the term that Bayesians use for a range that has 90% chance, or whatever percent chance, of containing the actual value. Now, this is one of the places where Bayesians and frequentists come to part paths. Ordinarily, if I were to ask the question, is it the case that there is a 90% chance that x is between 51 and 61? If you ask frequentists that question, the answer is emphatically no. They would say that x is not a random variable. X is a physical characteristic of a coin. It is what it is. It doesn't make any sense to make probability statements about it. In some rigorous logical sense, I suppose there's some logic to that, but it's a really useless conclusion to come to. So just purely on the interest of pragmatism, I would argue that, in fact, it is a reasonable choice to pretend that x is a random variable. And in that case, 51 to 61 is a credible interval that has a 90% chance of containing the true value, the true unknown value of x. So that's one way to summarize the posterior distribution. And all of this is great. This is the nice part of the Bayesian response, is that I'm willing to answer the question. The only thing that I have to acknowledge is that it's all based on the assumption that I made about the prior. And I started out by saying that I think the prior that I chose was pretty dumb. So we should loop back around and say about real coins. And now forget about urns and forget about probability class where everything is ideal. I want you to actually use the background knowledge that you have about coins. You could imagine that some coins have a sort of the head side might be convex and the tail side might be concave. I think I got those terms right. And so you imagine if you take it to the extreme that you could have a coin that deviates from 50%, but it doesn't seem like 1%. I don't think you could make a coin that has a 1% chance of landing heads, unless it was just a crazy coin. It would have to look like a bowl. Okay, so for ordinary coins, what do you think this range is like? Would you believe 55%? That doesn't seem crazy to me. So 55, 45, sure. 60, 40, maybe. 75 sounds like kind of pushing it. So we have information about this, and that's exactly the kind of information that you can put into a prior. One way to do that is something kind of triangle-shaped. I think that the values that are near 50% are much more likely than the values far away from 50%. So I could try something like this. So the blue is the prior that I used before. It's uniform from 0 to 100. The green is what I'm going to call the triangle prior. And it just says, I think that things that are near 50 are likely. I think 100 is impossible. 0 is impossible. Low things are unlikely, and so on. Okay. I don't know if this is right, but it's at least better. And one of the things that you often want to do is try out a couple of different priors and see how much effect they're having on your outcome. Also, be careful with the word posterior. So it can get you in trouble. So here's what that looks like. The blue curve is the posterior based on the uniform prior. And the green curve is the posterior based on the triangle prior. And you'll notice that they're superimposed on each other and almost indistinguishable except for a little hint of green up there. And what this says is that actually it doesn't matter very much what I choose as the prior in this case, because I have enough data that my posterior depends heavily on the data and not very strongly on the prior, which is a nice situation. It means we don't have to argue about whose prior is right. We don't have to get it exactly right. Anything that's even approximately is going to do fine. So this is called swamping the prior, and the notion is that with enough data, you can get reasonable people to agree, even if our priors are not the same, our posteriors will be the same. Okay, so it's a happy, peaceful world. However, with one exception, which is that if you give a probability of 0 to any hypothesis, there's no amount of data that will ever resuscitate that hypothesis. And you can see that mathematically because every time you do a Bayesian update, you're taking the prior probability, you're multiplying it by a likelihood. And so if the prior is 0, it doesn't matter what you multiply it by, the posterior is going to be 0. So as long as you and I agree to give non-zero prior probability to all hypotheses, we will eventually converge given enough data. This is the basis of what's sometimes called Cromwell's rule. You can read about this. The idea is, even if you think that a hypothesis is truly impossible, you should give it some arbitrarily small non-zero probability so that there is at least the possibility that data could persuade you. This comes from, the reason it's called Cromwell's rule is that Cromwell in 1640, I think, made a speech before Parliament in which he uttered this quote that gets quoted a lot: "I beseech you in the bowels of Christ, think it possible that you may be mistaken." That is, give it some, you can make it as low as you want, but non-zero probability, and I will eventually persuade you with data. Let me summarize where we are so far. In general, when you're doing this kind of estimation, you form a suite of hypotheses. I've written them H sub I, so there are a whole bunch of them. You choose some prior distribution where you give prior probability to each of your hypotheses. You compute the likelihoods, and then you turn off your brain. The good Reverend Bayes comes to your house, does all the work. He computes the posteriors for you. And that's what this framework looks like. Let us take a break. I think they're serving us food and drinks that we can run out. Because we took a couple of, I will say for the last half hour, you don't have any more work to do. I'll tell you some stuff, but we're getting toward the end of your work. Okay. So we started with this question that David Mackay posed, which was, do these data give evidence that the coin is biased rather than fair? And we did the estimation part of the problem, which is that we have now computed the posterior belief about what X is. But we haven't exactly answered this question because we haven't really talked about what it means to say that data are evidence in favor of a hypothesis or against it. So let me be more specific about that. In general, the Bayesian framework looks like this. We would consider data D to be evidence in favor of H if the posterior is higher than the prior. In other words, if having seen the data, my posterior belief is higher than my prior belief, then it's evidence in favor. Now, if you apply Bayes' theorem and do the math, you'll see that that is equivalent to saying that the likelihood of the data under the hypothesis is greater than the likelihood of the data under the not hypothesis. So twiddle H just means the complement of H. It just means H is not true. So I can compare these two values. These are the conditional likelihoods of the data, or I can compute the likelihood ratio. This is the likelihood ratio is the probability of the data under the hypothesis divided by the probability of the data under the complementary hypothesis. If that is greater than 1, then we would say that D is evidence in favor of H. That likelihood ratio is also called a Bayes factor. So this is the term we want to be able to compute. If we compute that factor, it tells us, first of all, what direction the data go in. Are they in favor of D or against, in favor of H or against H? It also gives us a measure of the strength. So if this is greater than 1, then it's in favor of H. If it's 3, for example, we would say, okay, it's in favor of H, it's not very strong. If it's 100, we would say that it's pretty strong evidence. I'll talk a little bit more later about how we're going to quantify that, how we're going to make those numbers meaningful. So let's do the coin problem. So we're going to have two hypotheses, F and B. F is the hypothesis that the coin is fair. B is the hypothesis that the coin is biased. And now we have to compute these two terms. These are the conditional likelihoods. How likely would the data be under F? And how likely would the data be under the biased hypothesis? Now, if the coin is fair, then I know that X is exactly 50%, and it's really easy to compute the likelihood of any given data set. That one's easy. B is hard because B is underspecified. So imagine this like a barroom bet. If you say you think the coin is biased, and I say I think the coin is fair, and we shout and we yell and we argue, and finally we say, all right, well, let's bet on it. I'm going to have to make you specify exactly what you mean by biased. I'm not going to bet with you until you solidify what you're talking about. So let's think about how we're going to formulate B. There's one really tempting version, which is that you could say, well, look, we got 140 heads out of 250 spins. That's about 56%. So I think that B is the hypothesis that X is exactly 140 out of 250. Now, if I made that claim, I suspect that you wouldn't bet with me. There are two reasons. So first of all, it seems like a total cheat that I'm going to use my data to form my hypothesis, and then use the data again to update my belief in that hypothesis. So something about that feels wrong. The other thing that feels wrong is if we do this, if I let you make that bet, you would find that any data set would be evidence in favor of B unless it was exactly 50%. If I got exactly 125 heads out of 250 tails, then the Bayes factor would be 1. But you would win all the other bets. That doesn't seem right. Okay, so we need some rules here. And all right, so here are the rules. You can have any hypothesis you want, but you have to state your hypothesis before you see the data. That seems fair. The other thing is that you can bet on as many values of X as you want. So you don't have to come up and say, okay, I think it's biased, and I think X is 42. You can say, well, I think it's biased, and I think X is between 40 and 60. And I have a belief about it that looks like this. So you can specify a prior belief about X as your way of telling me what you think B is. Okay, so that's what I'm going to do. This is, by the way, the same rules as roulette. Okay, you have to place all your bets before the wheel stops spinning. Hang on just 1 second. You have to place all your bets, and you can bet on as many numbers as you want, but for every bet that you win, you're going to lose some of your other bets. So you have to think about how much weight you're going to put on each of the numbers. Sorry, go ahead. could be, and in fact, one of the things that you often want to think about is where do these hypotheses come from? What data have you already used? And make sure that you don't double count. But let's say that I just gave you a coin and you've never spun it, but by examining it, you come to think that it might be biased. That might be what leads you to formulate B. And then we could honestly use data to update that belief. Okay, so we're going to play by roulette rules. Here's what roulette looks like in terms of likelihood, which is that you're going to give me a suite, where that suite represents your definition of B. How biased it is, you're going to capture that with a suite. We're going to update it using the data, and the way we're going to do that is by looping through all the hypotheses, computing the likelihoods, and then computing a weighted average over them. This is basically the payoff in roulette. The likelihood is the payoff. The probability is how much you bet on each number. And your total outcome is just the sum of the return on each bet times the quantity that you bet. That make sense? OK, so we're going to use average likelihood to compute likelihoods for these two hypotheses. So F now is going to be the hypothesis that X is exactly 50%. B is the hypothesis that X is not 50%, but could be any other value with equal probability. So I'm going to go back to that uniform distribution for now. We'll have a chance to revisit this. So you can think of this as uniform from 0 to 100 with a notch cut out of the middle at 50. That's what B is going to be. Here's what this looks like in code. So for the fair hypothesis, I'm going to create a suite, and I'm just going to put one value in it that has probability 1. This is a trivial PMF. It's just a deterministic number, 50% with probability 1. Here's what bias looks like. I'm going to loop from 0 to 100. I'm going to put every value into the distribution except 50, and then normalize. Okay. And here's how I compute the likelihood factor, the likelihood ratio, also known as a Bayes factor. So there's my data. Here is the likelihood of the fair hypothesis, the likelihood of the biased hypothesis, and then the ratio. This code is in euro2.py. So I want you to run that. We're going to run it once. We'll talk about what the results mean, and then you're going to modify it. So take a look, run it, think about what the results mean. Oops. So let me just do a quick aside. If you take a look at euro2.py, you'll notice that I've swapped in a different likelihood function. The data now, you remember in the previous version, the data was a long string that contained 140 H's and 110 tails. This is now a tuple that contains 2 integers. Oh, sorry, this is not correct. The actual data it's a tuple of 2 integers, the number of heads and the number of tails. And this is the likelihood of that particular outcome. It's x raised to the number of heads times 1 minus x raised to the number of tails. This is a slightly more efficient way of computing exactly what we did before. Here's the average likelihood function. We were just looking at that on the slide. There's the fair hypothesis and the biased hypothesis, my data. This is the likelihood of the data under the biased hypothesis, likelihood under the fair hypothesis, and there's the ratio. Now, you have to remember which way the ratio goes. So this is the ratio of biased in the numerator and fair in the denominator. So if this thing comes out to be greater than 1, what does that mean? that means that it's evidence in favor of the biased hypothesis. If this thing comes out to be less than 1, then these data are evidence in favor of the fair hypothesis. So if you run euro2.py, you get 3 numbers. Scroll that up. Make sure you can see it in the back. So the likelihood of the biased hypothesis is 2.5 times 10 to the minus 76, which is a ridiculously small number. And the likelihood of the fair hypothesis is also a ridiculously small number. This happens a lot with a lot of Bayesian analysis. When you ask, what's the likelihood of this specific data set under the hypothesis? The answer is often a very small number, because the chance of getting any particular outcome is quite small. But it usually doesn't matter, because we almost always care about these ratios, not the absolute likelihoods. In this case, the ratio that we care about is the biased hypothesis more likely than the fair hypothesis? And that number is telling us no. That in fact, these data are evidence in favor of the fair hypothesis. Yes, sir? Computing likelihoods, you compute log likelihoods, and it's manageable. An outcome as extreme as what we actually saw, or more extreme. Right. So just to repeat the question, so it's tempting, especially if you've had training in frequentist statistics, to think, what I really want to know is what's the probability that the coin is fair? And so what you described is computing a p-value. That's computing, if the coin is fair, what's the probability of seeing an outcome as extreme as what I saw, or more extreme? The problem is that that second question is not the same as the first question. The second question was, if the coin is fair, what's the chance of seeing what I saw? We want it the other way around. We want, having seen what I saw, what's the probability that the coin is fair? And it's exactly reversing the sense of the conditional probability. And this is one of the things that Bayesians in general don't like about frequentist statistics, is the bait and switch. Which is, I completely agree with what you said. The question that we want is the probability of the hypothesis given the data. What the frequentists compute instead is the probability of the data given the hypothesis. And even worse, they only compute one of them. They don't compute the other. So when you hear a p-value, in some sense, the p-value is the likelihood of the data under the fair hypothesis, with one difference, which is that I computed the likelihood of exactly the data we saw, and the frequentist computes the likelihood of those data or all the data more extreme than what you saw. So that was a lot, kind of a mouthful, but that in some sense that is the difference between Bayesian hypothesis testing and classical hypothesis testing. Good. All right. So the Bayes factor is about 50%. One way to think about that is if, before you saw the data, you thought that these two hypotheses were equally likely, then you would downgrade your belief by a Bayes factor of 2. And I won't show you how that computation works, but it's a straightforward one. it would take you from 50% to 33%. If the Bayes factor is a half, you would go from 50% to 33%. So it moves your belief, but not a super big amount. So a minute ago when I said that a Bayes factor of 2 or a half is considered evidence, but it's relatively weak evidence. Contrast that with a Bayes factor of 100. A Bayes factor of 100 would move you from 50% to 99%. So that's pretty strong evidence. That make sense? Okay. Okay, we ran Euro 2. We thought about the results. We got a likelihood of about a half, and that means that this data set is evidence against B, which is a little bit counterintuitive. Again, that's exactly why David Mackay chose this problem, because, again, if you look at the p-value says, well, these data are unlikely if the coin is fair. To which the Bayesian response is, well, yes, but they're also unlikely if the coin is biased. The issue is not whether the data are unlikely. The issue is the ratio. However, it was a little bit bogus, because when I formulated B, I deliberately formulated a dumb version of B. So remember, we're in this scenario with a barroom bet, and I put you onto a hypothesis that you probably didn't want, which is the claim you effectively said, I think X is equally likely to be anything between 0 and 1, except 50%. But that's probably not what you really meant when you said that the coin was biased. So here's your chance to redeem yourself, which is you can go into euro2.py and change the definition of B. Make the definition of B something a little bit more reasonable and see what you get. So here's the definition. Again, I stuck you with the full range of numbers from 0 to 100. That's probably not what you wanted. So try out some other variations. I'll give you a couple minutes, and then I'll ask you, what was your definition of B, and what did the Bayes factor turn out to be? Okay. I'll show you my example, and then I'll ask you for some of what you guys tried out. So the simplest thing to do is just to modify the range here. I did one from 35 to 65, and that's based partly on what we said a minute ago about what we think coins are likely to do. It's probably wider than you might want, but it's not crazy. So let's try that out. And with those numbers, I get this likelihood for biased, this likelihood for fair, and the Bayes factor of 1.6. So what does that mean? By this definition of B, how do I interpret the data? We would say that these data support the biased hypothesis. Not very strongly, but they do. 1.6 wouldn't move your beliefs very much. Again, if you started out at 50-50, you might end up at about 55 or 60 on the basis of that update. So it's not very strong evidence, but by this definition of B, the data would support B. Anybody else try out anything different? Different ranges? All the way in the back. Factor in that case is 5. 5.2, okay, yeah, so that's getting to be stronger evidence. But it's kind of a cheat, right? Yes? So still centered on 50, but narrower. And as long as you keep it centered on 50, that feels like a little bit less of a cheat. Okay, that's fair, yes? a nice idea. In some sense, that's like the crazy belief that this coin is unlikely to be in the middle and quite likely. And maybe that's one interpretation. If you say it's biased, if you had said, I think this coin is very biased, then the curve that you just described might be the right way to formulate that claim. Yeah. And so this is partly one of the things that you often do in Bayesian analysis is take things that people say verbally and try to quantify them in the form of hypothesis suites, either by formulating priors or by formulating the statement of a hypothesis. OK. So where we are so far, we've done the Euro problem, we've done Bayesian estimation, and we've done Bayesian hypothesis testing. That, by the way, is the Belgian Euro coin. We're not going to take another break. Sorry. I think we might have one more break before we're done. OK. Next problem I'm going to throw out is what I call a word problem for geeks. This is a hypothetical conversation between college students. Alice says, what did you get on the math SAT? Bob says, 760. Alice says, oh, well, I got a 780. I guess that means I'm smarter than you. So from a Bayesian point of view, what we want to ask is, given this data, what is the probability that Alice is smarter than Bob? Now, I wanted to bring up this example. I mentioned modeling earlier. Again, we're going to have to make some modeling assumptions. We're going to have to define exactly what we mean and figure out how to quantify this stuff. So here's the assumption I'm going to make for now, and we're going to come back to this later. Assumption is that each person has some probability of answering a random SAT question correctly. So if I pull a random question and I present it to you, you have a 95% chance of getting a randomly chosen question right. You have a 98% chance. Each one of you has some quantity p of getting a randomly chosen SAT question right. So p sub a is Alice's value. P sub b is Bob's. What we want to know is what's the probability that P sub A is greater than P sub B given these data. So let's walk through the process of doing that. So the first thing, again, we're going to treat P as a random quantity. I'm going to start by giving a prior distribution to everyone in the room. And then I'm going to use your SAT score to update that distribution. That's the plan. Now, this is one of those nice cases. Yes? So the question was that the SAT score is not the number of questions that you got right and that you got wrong. It is a scaled quantity. They report the percentiles, but the 200 through 800 is just a scaled score. So we're going to need to be able to map from the scaled scores back to how many you got right and how many you got wrong. The nice thing is that the College Board publishes that data. So we're going to be able to do it. The other thing that they publish is the distribution of raw SAT scores for everyone who took the test, which is a reasonable choice for a prior. If I don't know anything about you other than that you took the SAT, then this is my prior belief about your score. So this is one of those nice cases where we don't have to argue about the prior. This is pretty much it. The raw score. I also know how many questions there were on the exam, and that's how I get to P. So sorry, I skipped a few steps there, but that's where that comes from. The teeth come from the fact that if you get one wrong, they take off 1/4 of a point. So some quantities are more likely than others. Which is another simplification we're going to have to make. So this, again, modeling. You have to leave stuff out. However, the nice thing about this is that the likelihood function is relatively easy. In fact, it's the exact same likelihood function we just saw in Euro 2, which is if you give me the data here that are the data is the raw score. The raw score is, sorry, I'm not explaining this well. The data is going to be the scaled score from 200 to 800. I have a function that does the reverse scaling. So if you give me the scaled score, I can compute the raw score. I also know how many questions there were, and from that I can get yes, no, which is how many you got right and how many you got wrong. So that's the data. I have to do some massaging, but I can eventually get the data into a form of how many right and how many wrong. And I have the hypothesis, which is my hypothetical belief about your value of p. And now I can compute the likelihood, which is the same thing we saw before. P raised to the number that you got right, 1 minus p raised to the power that you got wrong. Make sense? Okay. So there's the likelihood function. And here's what the posterior distributions look like. So for Alice, it's the blue curve. For Bob, it's the green curve. So one thing we conclude, based on scores like 780 and 760, is that these people have a pretty high value of p. They're probably getting 90% of SAT questions correct or more. And it looks like the peak for Alice is a little bit to the right of the peak for Bob. And if I compute the mean of these two distributions, Alice's mean is a little bit higher. But that doesn't quite answer the question I wanted, which is what's the probability that Alice is smarter than Bob, where I'm just defining smarter as better at answering math SAT questions, which is, of course, what smart means. All right, so we're going to write a function called probbigger. It's going to take the posterior PMFs as arguments. So assume that it's Alice and Bob. And what I want to do is compute the probability that a value from Alice's PMF is greater than a value from Bob's PMF. There are a couple of ways that you could do that. One of them is just by random simulation. So PMF knows how to generate random values. So if you want, you could just run it 1,000 times, pick 1,000 values for Alice, 1,000 values for Bob, and just count how often Alice's is higher than Bob's. And you'd get a pretty good estimate pretty quickly, and that would be fine. We're going to be just a little bit more clever than that, which is we're going to iterate through all the pairs of values from the two distributions, check whether the value from PMF1 is greater than the value from PMF2, and count up the total probability of the pairs that have that property. And you're going to write this code in a minute. I'm going to give you a little bit of helper code, which is this is how you iterate through all the pairs in a PMF. There's a function called items that returns a list of pairs where each pair is a value and its corresponding probability. So this loops through all the values from PMF1. This loops all the values from PMF2. And your job is to compute the total probability of all pairs where V1 is greater than V2. And if you go to sat.py, you'll see again that I've given you the framework, and you can fill this one in. Just take you on a quick tour of the code. So read scale reads a file that I got from the College Board. And this is how I do the mapping from scaled scores to raw scores. Read ranks reads another data file that contains the raw scores for the entire population of people who took the test. Divide values is just a helpful function. I have an object called exam that contains all the information about the scores. And it contains both a lookup and a reverse function, so I could do a mapping in both directions. Here's the actual suite. So I have a suite that's called SAT that represents my beliefs about your value of P. It contains an exam object, so I know how to do the lookups. This is the likelihood function I showed you a minute ago. It uses that reverse function. And here's the function that you're going to write. Fill this in. Oh, look, I even gave you a total. Good, so it is 4:10, we are done at 4:40, so I have 2 bits of good news, which is we only have half an hour to go, and what this picture is meant to indicate is that your work is done. You have no more coding to do. I want to tell you about a couple more things, and then we'll wrap it up. So the first thing that I want to tell you about is the last case study that's in Think Bayes, which is a problem that's called the unseen species problem. And so I lied a minute ago when I said you had no more work to do. You have one more bit of work to do, which is you have to spot the unseen species. So raise your hand when you've seen the unseen species. The image here isn't so great, but if you've got the slide in front of you, you can find it. Let's see. Does that help?
Awesome to see up there.
It is up there? OK. Yeah, if you look at it on your own screen, you will find a giraffe there. That is not, unfortunately, the unseen species problem. The unseen species problem is if you go into an environment and you observe a certain number of species, the question is how many other species were there in that environment that you didn't happen to see? This is motivated in part by the Belly Button Biodiversity Project, which is a group of ecologists who go to ecology conferences, which are obviously a lot more fun than Python conferences, because what they did was collected swabs from the navels of all of the people who participated. They cultured those swabs and then did rDNA analysis on all the bacterial species that were growing in the belly buttons so that they could identify sort of species. Now, when you're talking about bacteria, the notion of a species is sort of fuzzy. And often when they do these sequencing things, they can identify it down to the level of maybe the genus or sometimes the species. So strictly speaking, I should say OTU for Operational Taxonomic Unit. But I'll just say species for now. So we'll assume that you collect data from belly buttons. And you want to know now, let's say that I observe 60 different species growing in your belly button, which was, by the way, the modal value. That was the most common outcome, was about 60 species. There was one person who self-reported that he or she does not bathe, and that person had 120 different bacterial species growing in his or her navel. Anyway, this is the formulation of the problem is we've seen, let's say, 60 species. We want to know how many other species were there that didn't show up in our sample. Turns out the Dirichlet distribution helps us out with this, which is if you knew exactly how many species there were, then I could get the prevalence of each species from the Dirichlet distribution. I won't go into the details of this. This is going to be a pretty high-level description of what this project is about. But I just wanted to give you a flavor of, by the end of Think Bayes, this is the kind of problem that you can solve with this stuff. So that's the condition that if you knew how many species there were, then you could compute the prevalence of each species. And from that, you could get the likelihood of the data. And that's the key to this whole thing, which is anytime you can compute the likelihood of the data, the good Reverend Thomas Bayes comes to your house and does the rest of the work for you. He can tell you the likelihood of the hypothesis under the data. Here's what that looks like. So what we're going to do is go through each hypothetical value of n, assume there are exactly n species, and compute the likelihood of the data. So just to make this a little simpler, if you go to a wildlife reserve and you start taking pictures of animals, and at the end of the day, you've seen 3 lions, 2 tigers, and 1 bear. I have no idea what kind of wildlife preserve this is, but you would conclude that there must have been at least 3 species there. But you might guess, how many more do you think there might have been that you didn't see? You only saw 6 individuals. There certainly could have been other species there. Now, again, we're going to have to make modeling assumptions and all that. All of this is usually based on the assumption that your chance of seeing any given species is proportional to the number of individuals, proportional to the prevalence. Or if you want to say it a different way, every individual on the nature preserve had an equal chance of being observed. Now, with megafauna, that's certainly not true, but with something like a bacterial swab, it might not be a terrible model. Here's what the posterior distribution looks like. If you started out thinking, I don't know, there might have been anywhere from about 3 to maybe as many as 30 species there, then your posterior, after seeing 6 individuals and 3 different species, looks like this. It says, well, maybe 3 is all there was. But it's actually more likely that there were 4, about the same likelihood that there were 5, and could have been 6, 7, 8, all the way out to about 30. By the time you get to 30, it's pretty unlikely. And so that's probably a good place to stop. This is another case, I think someone else asked a related question of, when you see a posterior that looks like that, it makes you think, well, the extreme values here were pretty unlikely. So in fact, if my prior had been much bigger, it wouldn't have mattered very much. There's just not very much likelihood out there. So 30 is probably big enough for this case. Yes, sir? It is a smooth curve, but this is a numerical approximation of it. This one is based on a very simple algorithm, and the presentation in the book goes through a process that I recommend quite a lot, which is I do a very simple version that is wildly inefficient and has a lot of numerical inaccuracy. But the nice thing about it is that it's only about 50 lines long, and it's demonstrably correct. You can look at it and convince yourself that it's right. What I then do is a lot of optimization to gradually make it faster and more accurate. But the nice thing is I can do a regression test against the baseline version. And for this problem, that actually worked out very well, because there were several steps while I was trying to do the optimization where I had bugs that I could only figure out because I knew what the right answer was. And if I hadn't, if I had deep-ended on the optimized version of the problem, I probably never would have been able to figure this out. Here's some actual data. This is not the subject who never bathes. This subject had, I think, 61 species. And this is what the data look like. So they've been identified. Corynebacterium, I think, is not a species, but a genus of bacteria. And there were 92 of them, on down to various ones. I've cut off the data. Again, there were 60 species. Many of them are singletons. There were many species where there was only one read that came from doing the genetic sequencing on these things. And there's really no such thing as a partridge in a pear triome. Here's what the posterior distribution looks like for people. So if I've observed 61 species, then I know that there can't be fewer than 61. In this case, it turns out that it's very unlikely that there are exactly 61. Having seen 61, my best guess is that there are about 72 or 73, but unlikely to be as many as 90, which kind of makes sense for what the data looked like. If a human being had been asked to guess, you would have said, well, there are so many singleton species that I think it's quite likely that there are others out there that didn't get observed. This is saying this is my posterior belief about one person.
Oh, okay.
And so this is actually for that particular subject.
Oh, okay.
This is if I went back and sampled that person's belly button again, how many more species would I find for that person? But certainly the related question is, if I now get a description of an entire population, I could answer questions like what you were getting at. These are the estimated prevalences. Now I'm plotting these in the form of a CDF, a cumulative distribution function. Makes it easier to visualize. If you are not familiar with CDFs, you can just close your eyes right now, pretend you're not seeing this curve. Don't worry about it. But what this is showing you is, for each species, what percentage of the population do I think is made up of that species? So species number 1, there were 92 of them. It is the most prevalent species that we found in this person's belly button. And so my conclusion is that the prevalence of that species is probably 20% of the population. It might be as few as 15%, and it might be as much as 25%. That's the high end of this dark blue distribution. The second most prevalent species is probably about 12% of the population. So that's what that figure is showing. So this is the posterior after we've seen the data. This is our posterior belief about how many species there are. And this is our posterior belief about how prevalent each of those species is. With those two posterior distributions, in some sense, we know everything there is to know about this subject's belly button. And if someone comes along and asks questions like what we were talking about a minute ago, if I go back to the same belly button and collect more samples, go back to the same environment. Broadly, this is all about environmental sampling. I go back to the same environment and collect more samples, how many more species will I find? Or more often what people care about is how many more samples do I need to collect in order to have a good chance of having seen almost all of them? I'm trying to achieve coverage. How much more work do I have to do to get coverage? I can do that by running some forward simulations. So given my beliefs about n and my beliefs about the prevalences, I can run forward simulations for up to, let's say, in this case, 400 samples. So if I went back to the same belly button, collected 400 samples, this is what the distribution, this vertical slice is the distribution of possible outcomes. It says if I run the simulation, sometimes I don't find any more. Sometimes I find 12 more. And the most likely values are in the 4, 5, 6 range. I've jittered these data by adding a little random noise to them. They're actual integer values, but by spreading them out, I make it a little bit more visible, although in this light, not very visible. So if I run a bunch of simulations, then I can generate a curve like this. So this table tells you how many more samples you have to do in order to achieve a given coverage. So this is what fraction, what coverage are you trying to achieve? So let's say you want 90% coverage. And you want a 90% chance of achieving that coverage. Sorry, 90% is up there. So you could read it off, and the answer is about 700. So what this chart is telling you is that if you go get 700 more samples, you will have a 90% chance of seeing 90% of the species. And you can read off this table to get whatever quantities you want. So this, in some sense, is the field guide for people who are doing this kind of ecological sampling. They know exactly how much work they have to do to achieve a level of coverage. One of the things I want to do with this is apply it to the Panamanian insect survey. There's an article about this. This, by the way, is the Belly Button Biodiversity Project. They have a nice page talking about all the work that they're doing, so you should check that out. wildlifeofyourbody.org. Did you? Oh, that's cool. Which one? I've been in correspondence with a couple of them. With data. Well, let me show you one other thing I've got going with this, which is when they published their paper, they desampled the data so that they had exactly 400 reads for each respondent or each subject. But they have more data for most of the subjects. So in fact, I can use their published data to generate predictions similar to the ones I just showed you, and then use their unpublished data to check and see if the predictions are right. So I've done the first half of that. If you go to alandowney.blogspot.com, you will find my blog. Where I've been writing about the Belly Button Biodiversity Project. And I've also been talking about transparency in science, which is the file drawer effect, is the tendency of people to do lots of experiments and only publish the ones that work. So in an effort to subject myself to public humiliation, I've generated a bunch of predictions and published them. And I haven't looked at the answers yet. So the next thing I do next week is spring break for me. And the first thing that I plan to do is open the envelope and find out what the answers are and count how many of these are right. This gives me a chance to talk a little bit about how you validate probabilistic predictions. So for each subject, I know how many reads they actually got. So they got 1,400 reads, but they only looked at 400 of them. And with the 400 reads, they observed, I'm losing my pointer. Well, if you read across the top row, they observed 48 different species. And so my predictions, those are the row across the top is the credible intervals. It's the 10% credible interval, 20%, 30%, all the way up to a 90% credible interval. What I'm saying is that I think there's a 90% chance that if I look at all the reads, we will discover somewhere between 1 and 9 additional species. I think there's a 90% chance of that. I think there's a 10% chance that the value will be exactly 4. So what I can now do with the actual data, let's say that the actual data comes in and it is 6. If the actual number is 6, then my 10, 20, 30, and 40 credible intervals were wrong, or don't contain the true value, and the 50, 60, 70, and 80 do. So I would score that by saying 0, 0, 0, 0, 1, 1, 1, 1, 1. And then I would add up the columns, and I would ask, how many of my 10% credible intervals contained the actual value? The answer should be 10%. Similarly, 20% of my 20% credible intervals should contain. So I'll be able to make a graph that shows how many should have been right and how many were right from 10 up to 90. And if it's a nice straight line from 10 to 90, if it is the identity line, then I win. And if it deviates heavily from the identity line, then I'm a chump. And I will have published my predictions and be very wrong. So you all have that to look forward to. The question is, can you use the data to predict whether someone bathes or not? The sample that they got only has one non-bather in it, but the number of species is kind of an outlier. So if you just kind of put a threshold at about 100 species, you'd do okay. Moving right along. One other application that I want to apply this to is what's called the Shakespeare problem, which is how many words did Shakespeare know? If you take all of the known works of Shakespeare, he used 31,534 different words in his writing. But he probably knew some other words that didn't appear. Oh, wait, sorry, no, I got that wrong. That's the total number of words he wrote. And then the number of different types. Sorry, I forget the details here, but the general idea is that you can think of the words that Shakespeare actually wrote as being a sample from the entire population of words that he knew. And in the same way that we estimate how many unknown species there were, we can estimate how many unknown words there were. Yes? Key spellings, right. So there's one question, what do you mean by a word? It's, are two different spellings considered two different words? And stemming is an issue as well, so yeah. One challenge with this is just scaling the algorithm up so that it works for larger numbers. Okay, we are almost done, and I'm going to take the recommendation of the tutorial organizers, which is to do the survey before you actually get out of here, because otherwise you won't do it. So we're going to take 5 minutes for you to do the survey, and then I will take 5 minutes to wrap up, and then we'll be done. Yes, for errors, you could estimate the number of unknown errors based on actual bug report rates, especially from duplicates. If the same bug is being reported many times, then that makes you think that there might not be a lot of undiscovered bugs. If every bug is only being reported once, then there are probably more. Very good. Okay, if you didn't finish the survey, you're welcome to do that a little bit later on. Last thing that I will do for only 5 minutes is just some suggestions about where you might want to go from here. I said at the beginning that one of the goals is that you should be prepared at the end of this talk to solve problems that are similar to the ones that we did as exercises. So I hope that's true. I also said that you would be prepared to go on and read other things. The first thing that I would recommend that you go on and read is my book. A lot of the examples that we've done so far today are in there. So if you have more questions about it, that might be a good place to start. As I said, the draft is available at thinkbayes.com. I would be happy to hear corrections and suggestions. Inspired by open source software, I keep a contributor list on all my books. So if you send me an email and I make a change based on your suggestion or correction, I will add you to the contributor list unless you ask me not to. Some of the problems that we've talked about, the Euro SAT problem and the unseen species problem, are all in the book. Some of the ones I didn't talk about that are in the book are the hockey problem, paintball, the variability hypothesis, and the kidney problem. I'll let you read about those. My students are currently taking a class working through the current draft of the book and helping me to revise it. And they're working on a set of case studies. Some of them are kind of cool. One of them is about fire. There's a particular sensor that people use to measure the heat flux coming off of fire and estimate how big the fire is. The problem is that when you're very close, if you're off by just a little bit in terms of distance, then your estimate will be way off. If you're far away, your estimates are better, but you're farther away. And so the balance between those two is to take a couple of different measurements at different distances and then use Bayesian regression. So that's a nice example. Collecting whale snot is a great problem. I'll have to tell you about that another time. If you're working on something similar to this, I would love you to write up a case study for it. My intent is to collect the best case studies and publish them as part of Think Bayes. I did a similar thing. I have a book that's called Think Complexity that has about 10 chapters that I wrote and then about 4 case studies that were written by my students. So if you have something like this, if you have a real problem that you're working on and you think that this framework might help, you could write it up, especially if it's something that stretches the framework a little bit and we have to add to it. If you write about a 5 or 10 page report, you could get it published. If you're interested in doing this, let's talk more about it. Another option, I'm always looking for fun projects to work on. So if you came here because you've got a particular problem that you're interested in and you would like my help with it, I can do that on an informal basis and just have some conversations and help you out. And if you want to do it on a more formal basis, I have some time coming up, including this summer, and I have a sabbatical coming up that I would love to spend working on crazy projects like this. So let me know if you're interested in talking about any of those possibilities. I think, in the interest of finishing up on time, I won't take questions right now, but after we break up, I'll stick around and answer questions. And we are done, so thank you very much.